Let me show you something I love in Unreal. It's inside any Niagara system, next to pretty much every property and attribute, and it's this little down arrow here. Today, we're going to unpack what it does, how it works, and how it lets us create amazing motion graphics. If you're new to this series, we're working on recreating the After Effects plugin called Plexus. It was used to create a lot of technical sort of motion design. I'm hoping to package it up into an easy to use blueprint. And if you're interested in that, you can sign up for more information. Link is in the description. Plexus, we already know it's done a lot of stuff involving dots and lines, but when you create a grid in Plexus, you can also add effectors. And these can do a lot of things like push apart or contain the particles. And right now you might be thinking, those new motion design tools in Unreal Engine, they can already do that. And you're right. However, I started to come up against things that Plexus can do, but the motion design tools can't. And so I've made it a bit of a goal for myself to learn more about how the motion design tools work. They're based off Niagara. And whenever you get into a new project, it's really good to have some kind of project to work on. And mine has been to recreate Plexus. There is this particular effector in Plexus called the color map. And this allows me to map the grayscale values of an image to whatever I want. In this case, position displacement. We're going to be recreating this today. As you may expect, the road to learning all of this contains a little bit of math, but don't fret. I've got a whiteboard. We'll try and break it all down. So we've got our particle system, Niagara, and we've got the idea of an effector that we want to try and enact. Now, there's a little bit of a difference in how things are kind of calculated. Like particle systems like Niagara, in general, in the simple systems, like all the disclaimers, but they just kind of read from top to bottom. Like you start off with an emitter, it spits out a bunch of particles, and then it does math on the particles bit by bit, and it arrives at a final position. And then that gets sent to a renderer, and that's what you see on screen. Effectors are kind of a little bit different. Like they are used to produce a position offset, and that position needs to be temporary. What do I mean by that? Like, let's say you have a simple effector, right, that says offset this particle by 20 units in the z-axis. Seems simple enough. You get your particle, you take its position, and then you offset it by 20 units. And repeat, right? You can see the problem, right? Every single tick, it's going to add 20 units right to position, then add 20 units the next tick, right to position, then the next tick, and the next tick, and it'll just fly off screen at a rapid pace. The answer is to use what's kind of like the concept of a rest position. We are going to store the position from before the effector. We're going to offset the position using the effector information. And then the next tick, we're going to restore the saved position before we get to the effector. We're in a blank project. We're starting from scratch. I've got a blank level here, and I'm going to right-click, create Niagara system, and I'm going to go looking for the minimal Niagara emitter template. Let's create that. Call it something like NS. And save, and I'm going to open it up, have a little look, and here is our minimal emitter. If you select that and hit F2, you can actually change it to whatever you like. Quick boilerplate, let's set this to GPU compute sim. It'll give us a warning, and we're going to set it to fixed bounds. And we're going to tick require persistent IDs just for the future. We'll probably need that for next tutorial if you know where we're headed. The fixed bounds I'll leave at -100 to 100 for the moment. In this emitter update, I'm going to make a spawn particles in grid. Now, Niagara is quite friendly in that, when it has an error, it will tell you what is wrong and give you a button to hopefully fix the issue. Luckily, you can see it will just give you what you want, but it's in the wrong position. Initialize particle needs to be before grid location, and then we'll be able to see if we set our sprite size down a little bit, now we can start to see our grid. And that is a 3D grid. Let's set this to 100 in the X and Y, just 1 in the Z, so it's a little easier to see. This is the stack we were talking about earlier, obviously. You remember it from the last tutorial. Niagara will work from top to bottom. We've got what happens when the emitter updates. It spawns the particles, and then as each particle spawns, it will get its location through this module here. So as we were talking about on the whiteboard, this is the section where we're going to want to store the position of the particle before we get to the effector's offset. But what we're also going to do is we're going to set up that variable in the particle spawn. So to do that, we're going to click this green plus next to the particle spawn. We're going to choose set new or existing parameter directly. And what's cool about this is that this module allows you to basically take any bit of data and assign it to another, or even create your own variables to use later. So it comes in blank with no parameters. We're going to come up here to this plus icon here, and now we can see all of the usual core parameters that you might be used to. So age, ID, mass, and we're going to be looking at particles position, but that's not what we want to write to. We want to make a new common position. This is the default that comes in when you choose position. So it actually will say, yes, you want to write to particles position? Nope, I want to go F2 and rename this to rest position. And it will default to writing the simulation position there, but this is where this little arrow comes in. This is what I was mentioning before. This little arrow is what lets you choose what you want to write into the rest position. And you can not only choose whatever you would like out of all of these different things that are positions, you can also come up with your own calculations to then push it onto rest position or even age position, all of the other kind of parameters that we have there. So what we're going to be doing here is taking particles.position and then writing it into particles rest position, effectively backing it up so that we have a copy of it pre-effector offset. Now, think about what we've just done. We've basically opened up the power to write whatever we want into this attribute. And you can do that to anything. Think about changing attributes like mass or viscosity or speed, acceleration. All of those can be controlled in this way. As an aside, this is what I love about Houdini. You can plug data from anywhere into anything else, and it unlocks technical craziness and new discoveries that really surprise you every time you get into it. Do you remember how I said I loved this thing? I mean, that's what I mean. I mean the procedural nature of being able to take data from here and plug it into here. This is the key to creating really interesting effects, and it's how you can control your outcomes very, very precisely. Now, if that still doesn't make any sense, don't worry. Best way to practice it is by doing it, so you'll hopefully pick it up as we go along. Now, the thing is, you may ask like, okay, I've done that, but how do you actually check that it has done that? Where are these attributes that you keep talking about? One thing you can do is come to this debug menu here. Click Attribute Spreadsheet. There's nothing here at the moment, but once you click Capture Single, this is basically capturing the data on every particle that's in the scene just for one frame. So you can see we've got all of those parameters that we were talking about, age, lifetime, mass. It has an inbuilt parameter called material random, which you can use in your materials to obviously provide some randomness. And as we scroll over, yep, there's our rest position, X, Y, and Z, and it's been written to from our position X, Y, and Z. So let's just check on our list of things that we need to do. We need to set this rest position in our particle update as well. I'm going to select this, hit Control C to copy, select the stage that I want to paste it into, and hit Control V. We've got the rest position on there. Let's add the offset. Obviously, there's still some more things to add later, but we'll start off with the offset so you can see what happens. If you're new to coding, a kind of tenet is that you want to break up your code into easy to understand blocks. You might call those functions. It's usually a good thing to try and make those functions generic. Generic in the sense of being able to be used in lots of different situations. So for us, that means I'm not going to try and put all of our code into this. Instead, I'm going to identify a simple process like adding an offset to a particle. And what we're going to do is we're going to set up inputs so that we can feed whatever we want into this offset, whether it be a texture sample or our spherical field. Now, we've just seen a module that can set parameters directly, but if you need to do something a little bit more complex, you can do it through what's called a scratchpad module. We know that it's going to be in the update, so we're going to hit the plus button here, and you can see that there is an option for a new scratchpad module. Let's click it, and although it opens up into a new interface, it also highlights the name over here, and we're just going to change it to add particle offset. So over here on the left, you can see we've got a map get node, which is where we can pull out any information that we want. And to do that, we can click the plus icon next to the pin, or we can even come over to our parameters where we can see our active overview, and we can drag whatever we need in here. We're going to need particles.position, so I'm going to drag that in here, and that's going to give us a pin that we can drag out and reference. Switch over to active overview, choose particles position, and we can click and drag it into the map get. Now this gives us a position that we can drag out and start doing things with. We know we need to displace it, so brace yourself for a little bit more math about how we're going to displace this. So every single particle is, at its heart, a 3D position. That means you can decide where it is inside this world space with 3 floats. To move it, we need 2 things. We need a direction that we want to move the particle in, and an amount to move it by, or a distance. The common way to describe a 3D direction is to use what is called a normalized vector. One way of thinking of a normalized vector is by imagining an arrow, which is exactly 1 unit long. And we can describe the direction that's pointing in by describing the position, those 3 floats, the vector 3, of a point at the tip of this arrow, exactly 1 unit long. Now, if this was pointing directly up, which in Unreal is the z-axis, it would be at position 0, 0, 1, because we're just going up in 1 unit on the z-axis. If we're pointing in the x-axis, that's 1, 0, 0. Pointing on the y-axis, that's 0, 1, 0. And of course, it can rotate anywhere around that 0, 0, 0 point to give us a direction. Now we've described that using a vector 3, we need the length that we're going to travel, or because that's a very specific mathematical function word, I'm just going to say distance. So we're going to need the distance that we're going to be traveling. And that's pretty simple. It's just a float. It's as if you got the original position of the particle, the final position after the effector, and just pulled out a tape measure and figured out how long a distance it is between them. So maybe like 20 units or 25 units or something like that. Now we've got those 2 things. We've got a direction to head in, and we've got a distance. We can now work out our new position mathematically. All we have to do is multiply our direction by the distance we need to travel, which mathematically that gives us a new vector 3. And then we add that new vector 3 to the original particle position. And what that'll do is translate it from its original position to its affected position. So let's transfer the math from the whiteboard into this scratch pad. We're going to scale the distance by multiplying the amplitude by the distance. Then we're going to multiply that distance by the vector. So that's our direction there, and then that's multiplying by how far we want to go. And that result can then be added to our position to translate it from our original position to our final offset position. Now you may have noticed that the particle.position is not a vector as well. It's its own data type. It's a position. which I will leave to, somebody like Thomas Thal VFX, who explains it way better than I could. So I'll leave a link to it in the description. But the most important thing that you need to know is that the longer you can keep a position in its initial precision, so it's very, very precise the way it is on this pink line here, and the longer we can keep this through line going, the better. An add node won't take two positions for some reason, so you definitely need to make sure that this second node is converted to a vector before you connect it up. Now we've created it and you've made sure that you've saved, there is another thing that we actually need to do. If you ever create a scratch pad, you need to make sure that you hit the apply button. And it's in a kind of weird place. It's here. And it's also up here. And there's also a compile button. There's a lot going on. Biggest, most important thing is whenever you create a new scratch pad, make sure you hit this apply button. But without it being applied, it won't do anything once you go back to the system overview. Now, to get back to our system overview, you can come up to these tabs here, click the system overview, and we can have a little look at our preview. Now we can add our displace vector to here, and we can set it to 001, so it's just pointing straight up. We can set the amplitude to 1, so that'll just pass through the distance. And as we increase this number, I said earlier it would fly off, but it's not, and that's because down in the timeline, I haven't clicked play yet. So once you've clicked play, you can see by adding any kind of displaced distance, it is flying off into the stratosphere. So we definitely always need to make sure that we are setting the particle's position from rest position before the rest of the update. So we have a module which can displace the particles. That's good, right? And what can we do that? Well, now we're on to the fun stuff. We've set the stage, and the rest of the tutorial will be me showing you how to implement that color map that we showed at the beginning of the tutorial. So when we're talking about texture sampling, whether it's on a model or elsewhere, requires two coordinates, UV coordinates, and they're expressed as a 2D vector going from 0 to 1. So you'll have two floats, each capped at 1. Given we're setting up the particles in a grid, we want the X and Y coordinates to be mapped to our UV coordinates so that we can place an image across the grid like this. And when I was setting this up, I suspected that the grid location should provide some kind of UV coordinate because it's got all of the information in this X, Y, Z count. As it goes through and then provides position for this particle, it would have the UV coordinates inside. Luckily, if I have a little look through the parameters down here, scroll down to module outputs, you can see that the grid location has a UVW coordinate. You may have caught that's got another letter. That's not just a UV coordinate, it's a UVW. A 3D UV coordinate, that's a whole nother rabbit hole. But all we need to do to get a UV coordinate like we want is to truncate it, to chop off the W. So let's put a pin in that for the moment. We can get a UV coordinate. We also need to sample a texture, and we know that we want to do it in the update section so that the texture can change every tick. We're going to click plus, going to go to sample texture. And they have one perfectly available, and everything disappears. What I've discovered is that it doesn't seem to work for the sprite renderer, but what you can do is change over to a mesh renderer. And instead of the usual gnomon, I'm just going to change it to the 1 unit sphere. And I'm just going to go back to my initialized particle, and I'm going to set the mesh scale to be a little bit larger. So I'm just going to set it about that size, and that should be working. It's using the default material. So I'm just going to change it back over to a very simple material, which we made in the first tutorial, but let's just remake that really quickly. I'm just going to right click, create a new material, open it up, and all I'm going to do is add a particle color node and hook that up to the base color. Now I'm going to enable material overrides, and I'm going to override the sphere material Okay, it is no longer using the world grid material. I have a texture, which I chose because it's got a gradation from black to white, and so we can use that for a height displacement. Unfortunately, it's not showing. We haven't yet put in the UVs here. So we'll come back to where we've got our active overview of all of our parameters. So what I've just tried to do here is making a vector 2D from this, but it doesn't seem to work. And I think it's because of this namespace. This namespace here, if you hover over it, explains it's a transient value that doesn't persist between stages. So perhaps because it's being set up in the particle spawn, it's not persisting through to the particle update. So what I'm going to do is I'm going to do what we did before by setting a new or existing parameter directly, and I'm going to create my own vector 2D, common vector 2D, and I'm going to call that text UV. But what you can also do is do like a mini scratch pad. We're going to do that this time. I'm going to come down here to new scratch dynamic input, click on this, and you'll see that it's opened up a new interface again. It's very familiar. It's very much like this one. It's got one input and one output, and the output is already set to the type that it's expecting. It gives us a default input, which is actually coincidentally the correct thing that we need. So I'm going to say this is going to be the UVW input. And all I'm going to do is break it, break vector, and I'm then going to make a vector 2D. Connect the X and Y to there, and I'm going to drag the output. I'm going to hit apply. Let's come back to the system overview. You'll find that we have this new input here, and all we need to do is set this to be our grid location, grid UVW. And back in our sample texture, make sure that it's set to use the text UV particle attribute as its sample. Now it is showing up. And one interesting thing that I just found out is that the sprite renderer still actually does work. It's just, it's interpreting the alpha channel as well. Whereas on the mesh renderer, we actually get black. Okay, so we're sampling a texture and we're applying it to the color. How do we send that over to the particle offset? We can do another take the data from over here and plug it into here by going to our particle offset and using the sampled color. So the intensity would be from 0 at black to 1 where it's white. We can use that as the displaced distance, and that's calculated per particle, remember. So if we come over to the parameters window and have a look in the active overview, you can see that in the particles namespace, sample texture has actually written quite a few. We've got the sampled color, which is the full linear color, but you've also got this sampled R, G, B, and A, which are all floats. You can tell that this is a float because of that green there. So if I just drag this sampled R over to our displaced distance, let's crank up the amplitude. And now we're getting where the particles are white, it's displaced the most, and where it's black, it's displaced the least. It's now acting like Plexus's color map. We can take the data from the sample texture and use it however we want, whether it's displacement or applying it directly to the color of the particles. If you followed me this far, thank you. I hope it's been useful. I hope you found it easy to follow along. The next one will be joining the dots with lines and putting the final touches on the Plexus interface. And the cool thing is that I'm actually building this now. I've decided to try and put it into a blueprint to make it easy for everybody to use. And if that sounds interesting to you, there is a link in the description with more information. In any case, thanks for following along. I'll see you in the next one.